Okay, so it's my great pleasure to introduce Henry Yuen, and he will talk about testing low-degree polynomials in the non-commutative setting.
All right. Hi, everyone. Yeah, thank you, Guo Liang, for inviting me to speak at this seminar, and thanks to everyone for coming to my talk. So I was looking through the list, this really impressive list of talks on the global NCG website. And I think this talk is going to be a little different than what's usually discussed in the seminar for a couple of reasons. One is that low degree testing is a topic from theoretical computer science that, to my knowledge, hasn't yet been explored in non-commutative geometry, as far as I know. And the other, maybe more conspicuous reason is that I'm using a PowerPoint presentation instead of Beamer. But despite these differences, I hope you'll find this talk interesting and accessible. So this is based on joint work with Zhengfeng Ji, Anand Natarajan, Toma Vidic, and John Wright. So let me start by giving a general overview of low degree testing in the classical or commutative setting. So let's say that you have a finite field F with some number Q elements, and you have some multivariate function F that maps F to the M to F, and let D be some degree bound. And for now, just imagine that D is much, much smaller than Q, the size of the field. Let's imagine that the way we're given access to this function F is through this black box or blue box. And we can only make local evaluations to this function to see what the value is. So you plug in X and then you get F of X out. So a basic question is, how many evaluations of this function F are needed to determine whether F is a degree D polynomial? So just to be clear, by degree, I mean the maximum monomial degree in a polynomial representation of F. And since we're working over finite fields, every function has some polynomial representation with large enough degree. Just as a simple example, this polynomial f of xy equals x to the 10, y to the 5, plus y to the 10. This is a degree 15 polynomial. So if you're only allowed to make these evaluations to f in this black box manner, how could you tell if it's a degree D polynomial? In the worst case, if you wanted to be 100% certain, you would have to evaluate f on all the points in this vector space f to the m.
When you say degree D, I guess you mean less or equal to D.
Yes, at most D, sorry. So not necessarily exactly equal to D, but at most a degree D polynomial.
Yeah, I agree.
So let's think of querying all the points in this vector space as being expensive. But let's say you wanted to make fewer evaluations. And by choosing the points that you evaluate f on randomly, and you allow yourself some probability of error, you can actually test this property of being low degree or being degree D using much fewer evaluations. So you can do that using this low degree test. And it's a very natural test. So here's one way of doing it. Let's say you pick D plus 2 random collinear points in this vector space. And by collinear, I mean that they all lie on an affine subspace of dimension 1. So you pick these D plus 2 points, and then you plug them into the box and you obtain these evaluations, A1 up to AD plus 2. So you take the first D plus 1 evaluations and you interpolate a univariate degree D polynomial, h of z, through these points. And since you have D plus 1 points, this uniquely determines a degree D univariate polynomial. And then you just check whether this polynomial, this univariate polynomial is consistent with the very last point that you queried on this, the D plus second point. And if so, then you accept, otherwise you reject. So it's a natural test. It's easy to see that if f were truly a polynomial with degree D or at most D, then because restrictions of of f to any one-dimensional subspace yields a degree d univariate polynomial, such a function f would pass this test 100% of the time. And it's not too hard to see that, conversely, if you have a function that passes the test with probability 1, then f must be a degree d polynomial as well. And so this, this low degree test is, it basically gives a local characterization of what it means to be a degree d function, right?
As long as one means always, I suppose. Yeah, of course,
always
it's
with
finite.
probability.
Yeah, sure. Yeah,
that's right. Yeah. So that's nice, but a more interesting question is, how robust is this test? Suppose that you had a function f that passes this test with probability p that's maybe less than 1. Can you deduce anything about the structure of little f? And it turns out that you can say something interesting. And this is what we call a low degree testing theorem. So this is an example of one by Aurora and Sudan from the 90s. So if this test passes with probability p, then there must exist a degree d polynomial g that agrees with f on roughly p fraction of points. And here you choose, the way you measure agreement is you choose a uniformly random point from your vector space and check whether the two functions are equal. And so, the kind of remarkable thing to notice about this is that here, this probability p can be very, very small. As long as p is greater than this quantity, O of degree over field size raised to some power, which is some very, very small number, we still have some guarantee on the structure of f. We know that at least on some part of the space, it looks like a degree d polynomial. And so we say that f has, roughly p agreement with g. So just to put things in a nice picture, let's say we have some cartoon, which is this function f, and our goal is to test whether f is a linear polynomial, degree 1. So just by the way I've drawn it, you can see that it's clearly not a linear polynomial, but we don't see f in its entirety. We only see local pieces of it. And we can see, at least in this part, f is trying to pretend to be a linear polynomial, but in other parts of the space, it behaves, in a more complicated fashion. So let's say we ran this through the low degree test, and suppose we picked 3 points, x1, x2, x3, as shown. Then when we get the valuations of f and we interpolate this univariate polynomial h, we get this line, and it so happens to agree with f, right? And so in this case, the test would pass, and you would erroneously believe that f was indeed a linear polynomial. But on the other hand, with other probability, let's say you picked some other points and you perform the test, you would see a mismatch between the interpolated polynomial and the function f. So the test would reject. All right, so that's low degree testing. And let me just briefly mention, where does it come from? Why is it studied in computer science? So it was motivated by applications to complexity theory. And so I think the first instance of low degree testing came in this work in the early 90s by Babai, Fortnow, and Lund. And they analyzed something called the multilinearity test. A test to, you want to test if a function is multilinear. And they use this to obtain a complexity result known as MIP equals nexp. Okay, I won't explain what that means, but that's where it first showed up. And then there was a lot of other applications in program checking, something called probabilistically checkable proofs. And each of these results relied on obtaining better and better low degree testing theorems. And so that was, a lot of this work came in the 90s. And in the 2000s, people started just studying low degree testing as just a mathematical phenomenon in itself without necessarily, applications. And there's lots to be said about it. Let me quickly explain maybe one of the highlights of the applications of the low degree testing theorem, and that is this probabilistically checkable proofs, or PCP theorem. Excuse me. So this is what it says. It says that every mathematical proof, maybe you express it in ZFC, of some length L can be efficiently encoded as some new string that's of slightly larger size, some polynomial size in L, such that the correctness of this proof can be checked with high probability by only examining a constant number of symbols of this new encoding at random. And here by constant, I mean independent of this length L. Okay, this is a rather remarkable theorem. In pictures, let's say that one day some aliens came down to Earth and they had, they claimed to have an enormous proof of the Riemann hypothesis. And of course, we would be very, very, very interested in learning about it. But this proof is, inscrutable. It's very, very long. But the PCP theorem allows us to go back to the aliens and say, why don't you provide us a PCP encoding of your proof? And we can check just by examining, a constant number of symbols of this proof at random to conclude whether your proof was valid or not. And maybe we would conclude at the end that we believe that the Riemann hypothesis is true. So quite remarkable. And low degree testing theorems are crucial to the proofs of the PCP theorem. Today, we know of alternate proofs of this PCP theorem that don't use low degree testing, but really in the early days, they were very, very essential to proving this. So to give you a sense of how low degree testing plays a role in proof checking, here's an equivalent formulation of the PCP theorem. So let's say you start with a ZFC statement X. It could be true or could be false. We don't know yet. But given this statement, we can efficiently transform it into a polynomial in some number of variables. So let's call this polynomial phi, and it has some variables x1 up to xm, and there's these extra variables y1, y2, y3. It's a polynomial of degree order of m over some finite field whose size is polynomial in M. Okay, so M is a number that we choose. And what is the property of this polynomial phi? Well, it turns out that X has a ZFC proof of length L at most 2 to the M if there exist multilinear polynomials in M variables, such that if you substitute these polynomials A, B, C into the last 3 coordinates of phi, as a polynomial, you get the identically zero polynomial over this finite field. We have this transformation. You can perform it in polynomial time. Like you can write a computer program to do it. So what does this PCP proof of a statement X look like? Well, it consists of evaluation tables of these supposed multilinear polynomials A, B, and C, if there exists one. So imagine that we have this person here who's interested in whether X is true. So the aliens can come down and provide these evaluation tables of these multilinear polynomials. They're just the evaluations of these polynomials at all points in the finite in this vector space f to the n. And now, if we want to test the validity of the proof, if we want to know if it's corresponds to a correct proof or not, the verifier will pick a random point in the vector space and plug it in first into these evaluation tables A, B, and C, get the valuations, and then plug that into this polynomial phi. Okay, and check whether it's 0. So this part of the test only requires one query, one evaluation of each of these functions, A, B, and C. But the second part of the test is, well, we want to actually check whether A, B, and C correspond to multilinear polynomials or low degree polynomials. So this verifier here can make a few more queries about log L queries to A, B, and C to test whether these evaluation tables actually correspond to multilinear polynomials. So why does this work? So let's say that there were the evaluation tables at A, B, and C. We don't know for right now if they actually are low degree polynomials or not, but there's some evaluations. Let's say they pass this test with probability 1 minus epsilon. You can think of this as like 99%. Well, since they passed this low degree test, by the guarantees of the low degree test, there must exist bona fide multilinear polynomials, A tilde, B tilde, C tilde, that are close to these evaluation tables, right? That's what low degree testing gives us. And now, since, when we plug in a random point into these A, B, and C, and then you put the valuations into this low degree this polynomial phi, you get 0. By a triangle inequality, you know that if you evaluate it instead at these A tilde, B tilde, C tilde, that the following condition holds, that this polynomial phi actually vanishes quite often. All right, so this is what we know from this high acceptance probability. Well, let's notice one thing. If we take this polynomial phi and plug in A tilde, B tilde, C tilde, this is still a low degree polynomial. It has degree O of m. And one thing we know about low degree polynomials is something called the Schwartz-Zippel lemma. It says that a non-zero degree D polynomial over F can vanish on at most D over size of the finite field fraction of points, right? And here we're thinking of D over F as being a very, very small quantity. On the other hand, we know that this polynomial vanishes on a large fraction of points. So therefore, this polynomial must actually be the identically zero polynomial. And by construction, this means that X must be true. It has some proof of length L. So this is how you can probabilistically check whether a proof is true or not. And if you want to improve your confidence, you can just repeat this test O of 1 over epsilon times. And the total number of queries that you've made to these evaluation tables is something like logarithmic in L, which is much smaller than checking the whole proof of length L, right? So you've saved yourself a lot of work. So this is one application of one very important application of low degree testing.
Is the finite field F fixed by the problem, or can you choose it?
There's some freedom. Basically, it just has to be large enough for such, it has to be a large enough size that it's larger than logarithmic in the length of the proof that you're interested in. So
the degree over the base field is not fixed or anything like that.
It's a choice that's made by the transformation. So for every m, I can have a transformation that has this property.
Yeah. Okay.
Yeah.
But what I mean is that F, you couldn't always choose, for instance, F to be Z mod PZ for a prime, or could you?
Oh, yeah. You can always assume that it's a prime field, for example.
Okay.
Yeah.
Okay.
That's not so important. Okay, so this is all in the classical setting, and I think it's very nice stuff, just to provide some background and motivation for where it comes from. So let's turn to the non-commutative setting. All right, so before, we imagined that this function f was represented as some box. You plugged in a point into this box and you got some value out. And the box was really just, inside the box, there's really just a giant table of numbers. It's like the evaluations of this function. But in the non-commutative setting, we're going to generalize this a bit and say that this box, what it's doing inside is not necessarily reading off numbers from a table of numbers, but maybe it's doing some physical process called a measurement that produces an outcome with some probability. So how do we model that? Well, let's define a measurement M with some outcome set S to be a collection of operators, M sub s, so these operators are indexed by the outcomes, where each of these operators for projections on c to the n for some integer n. So here in this talk, we're only going to focus on the finite dimensional setting. And when you sum up these projections, you get the identity.
Self-adjoint projections or not?
Yes, self-adjoint, sorry, yeah, self-adjoint. So that's the mathematical description of a measurement. Now, so inside this box, when it performs a measurement, it yields an outcome we're going to define it with probability, the tau norm of ms squared. So this is the probability of yielding outcome little s. What is the tau norm? It's just another name for the normalized Hilbert-Schmidt norm. You can see that if you sum up these probabilities, you get 1. This comes from the completeness relation on these s's. What if you wanted to perform a sequence of measurements? Well, then let's say you have M1, M2 up to MK. Then this yields some outcomes, S1 up to SK, with probability that is the tau norm squared of the product of these measurements. And this is where the non-commutativity comes in. These operators don't, these measurements don't necessarily commute. And the motivation for this formalism comes from quantum physics. This is kind of a very special case of measurements on a quantum system. We can imagine that inside this box, there's a particle that measurements are being performed, and these probabilities correspond to the outcomes if you actually measure this particle. All right, so let's say you had a quantum box instead of a classical box, and we tried to perform low degree testing on it. So like I said before, this box in the classical setting had some fixed table of numbers inside, but now let's instead assume that every time you plug in a point into this box, it performs a measurement and outputs something with some probability. So in this non-commutative or quantum setting, there's some underlying dimension n to your measurements. And for every point in the vector space, there is an associated points measurement. And when you make a points measurement, it returns a value in the finite field. Okay, so that's what's going inside this box. We can also query the box with a sequence of points, x1 up to xk, and we get a sequence of values a1 up to ak in this finite field out. And these outcomes are random, and the probabilities are given by this, this norm. So, okay, so that's the setup. Now let's imagine that we performed a low degree test with this box. We're given these points measurements. Again, we pick d+2 random collinear points, but instead of getting these deterministic evaluations, we get some random evaluations out with some probability. And we do the same thing. We interpolate a univariate degree d polynomial through the first d+1 points, and we check whether this polynomial is consistent with the last point. Suppose this test accepts with probability p with these measurements. What can we say about the measurements? What structure can we deduce about them? Can we somehow deduce that they're globally consistent with low degree polynomials in some way? Well, let's look at the commuting case just to start orienting our intuition. Well, I claim that it's exactly the same as the classical setting. So let's suppose that all of these measurement operators commute for all possible choices of x and y and outcomes a and b. Then since they all commute, we can all diagonalize them simultaneously. So without loss of generality, they're all diagonal matrices with entries 0 and 1 down the diagonal. And then we can, from this, I claim that we can define classical functions for each of the diagonal entries. So for example, f sub I of x is equal to a if and only if the ith diagonal entry of this operator is 1. And if I define the these functions this way, then the distribution of outcomes from performing these quantum measurements with these commuting measurements is just uniform over these deterministic values. You can imagine that the box first samples f of I for a uniformly random I, and then once that's fixed, just evaluates f sub I on the requested points. All right. So in this simple case, in this commuting case, if these measurements pass the low degree test with probability p, we can just directly apply the classical low degree testing theorems that we know of and deduce that, for example, on average over a uniformly random index I, f sub I has roughly p agreement with some degree d polynomial. Mm-hmm. Okay, so that's, tells you at least, even though we're in the matrix setting, there's still structure to these matrices, and they really just look like direct sums of, classical functions f sub I. Here's another way to express this. We can define a global measurement. So this is a single measurement S with outcomes, and it's a measurement that produces outcomes that are functions. And we can define as S of F just to be the product of these individual points measurements that are consistent with that function. And since these operators all commute, the order doesn't matter. So this S sub F is still a projection. What we can say is that, also equivalently, like each points measurement is really the marginalization of this global measurement. So AXA, this points measurement, is really the sum over all, global measurements S that on X produce A. Okay, so these are all equivalent statements. And if we know that these points measurements pass the low degree test with some probability P, then we know that these global measurements have good correlation with the set of low degree polynomials. So if you summed up the mass of all the functions f that have P agreement with degree D polynomials, then the mass of this is at roughly at least P. Okay, so this is in the commuting case. It's just like the classical setting. And so this tells you, with these matrices, there's still some underlying global assignment to all the variables, but maybe chosen in some probabilistic way. But what happens when these measurements do not commute? Of course, that's the interesting setting. And so let me give a simple illustration of how, when you have non-commuting measurements, there isn't necessarily an underlying global function that explains the outcomes. And so this takes me to something called the magic square game. But before I go on, are there any questions about what I described so far? Okay, so let's talk about the magic square game. It's kind of a simple game. So we have a 3x3 square with 9 variables. And the goal of this game is you want to assign 0 or 1 values to each of these variables such that it satisfies these constraints. So all the row sums must be 0 modulo 2. The column sums must be 0 for the first 2 columns. But the last column, if you sum up the variables and you take the sum mod 2, you must get 1. So it's not too hard to see that it's not possible to assign 0 and 1 to all of these variables in a way that satisfies all the constraints. Because if you sum up all the rows, you're supposed to get 0, whereas you sum up all the columns, you're supposed to get 1. So it's not satisfiable. Let's imagine that, again, we have a box, and we want to see whether this box is capable of assigning values to these squares that satisfy the constraints. So to this box, we can plug in variables from a row or a column. and the box is supposed to output assignments to the variables in that row or column. Okay, so you only get local views of this magic square. And then you test whether these output values satisfy the row or column constraints. So, we can plug in the first row, or we can plug in the middle column, and so on. Okay, so from what I said before, it's not possible for this box to satisfy all the row and column constraints if this box has a fixed assignment to the variables. Okay, but on the other hand, if this box made quantum measurements, then there actually exist measurements that can make measurement operators that are 4-dimensional, that measure points in a row or column that always, with probability 1, yield output values that satisfy the row or column constraint with probability 1 always.
Is this related to the example of Mermin and Coleman on spin systems?
Exactly. So this magic square game is also known as the Mermin-Perez magic square game. So,
okay.
So he came up with it, yeah. And what do these measurements look like? Well, they actually consist of non-commuting operators. So if, for example, you took the measurements that corresponded to the points x1 or x5, it turns out that they look like these matrices. These are anti-commuting operators, so the measurements don't commute. And so the moral of the story is that these non-commuting measurements can pass this test with 100% probability, but so therefore they cannot be consistent. These measurements cannot be consistent with a global assignment to all the variables. So let's go back to low degree testing. This magic square example suggests that in order to try to say something about the structure of these points measurements, we have to make some slightly stronger assumptions. So let's assume that the points measurements don't exactly commute, but they approximately commute. And I'm going to measure this in the following way. It's going to be on average over a uniformly random 2 points x and y from this vector space f to the m. I'm going to sum over all the outcomes and look at the normalized Hilbert-Schmidt norm between of their commutator. And let's say that this is at most epsilon. And let's also say that these measurements pass the low degree test with probability p. Can we now say anything about the consistency between these points measurements and low degree polynomials? So for small enough epsilon, we can draw non-trivial conclusions. So here's a warm-up. Let's say that we're extremely close to commuting. If we're close enough, we can actually reduce to the commuting and therefore the classical case. So, let's say that, okay, so this fact is true. So if we have almost commuting measurements, then we can relate them, perturb them to exactly commuting measurements, let's call them b to the x, such that the difference between the original measurements a and the new measurements b is at most k times epsilon. What's k? It's something horrendous. It's doubly exponential in the size of the vector space, 2 to the 2 to the o of q to the m. Okay, and this is this, you can deduce this from some rounding argument like from Filanov and Kashkovsky. So this is a pretty expensive price to pay for this rounding, and so therefore you can't say anything interesting unless epsilon is doubly exponentially small. But if it is, then by passing over to these exactly commuting measurements, since these b's were close to the a's, they pass the low degree test with probability that's close to p. And we then use what we know about exactly commuting measurements to say that, well, there must exist global measurements S sub f that has correlation with low degree polynomials, and they're also consistent with the original points measurements. Okay, but this is kind of trivial when epsilon is anything that's not super tiny. So you'd like to prove something for larger epsilon, hopefully independent of Q and M. So this brings us to the main result that I wanted to talk to you about. So this is from joint work with G, Natarajan, Vidic, and Wright. So fix an epsilon and fix these parameters, the vector space dimension M, degree D, field size Q. And let's say you have these measurements that approximately commute in the way we have before. And something called the low max degree test accepts with probability 1 minus epsilon. So here, this is in like what we call the 99% regime. We only, we don't know anything if it passes with low probability, but if it passes with high probability, then there exist measurements, these global measurements that outputs a max degree D polynomial such that, the points measurements is delta consistent with SF on average. So consistency here is that the points measurement is close to the marginalization of the global measurement by this error delta. What is the error? Well, it's this quantity here. So let me point out some features of this theorem. So first, we're using a different measure of polynomial degree. And this max degree is the maximum degree of any variable in a polynomial representation of f. So here, we take the same polynomial here. This has max degree 10 because the maximum degree of the variable is 10. We're going to use a modification of the low degree test called the low max degree test. Like I said, this test only works in the high probability regime. But the important thing is that we get a non-trivial statement with epsilon is 1 over polynomial in M. So epsilon doesn't have to be doubly exponentially small. It only has to be polynomial small in the vector space dimension N. Okay, so what is the low max degree test? It's exactly the same thing, except we're picking D plus 2 axis aligned points. Okay, and basically point is axis aligned if the direction that the line goes in is one of these elementary basis vectors. Okay, so I'll just draw a picture because it's just easier to see. These green lines are axis aligned. This red line is not axis aligned.
So you mean the notion of degree that you have depends on the axis, of course. So I mean, it's not invariant in the transformations.
That's right. Yeah. And so, it's also not too hard to see that if you have say a classical function that passes this low max degree test with 100% probability, then f must have max degree D. Mm-hmm. Right. So it's this is a local characterization of max degree D. Okay. What about the robust case? If this function f passes this test with probability 1 minus epsilon, then f has 1 minus delta agreement with a max degree D polynomial, where this delta is the same quantity we saw before. And this is arguably the first low degree testing theorem that was proven. This is by Fortnow and Lund. And so essentially we're proving a quantum version or a non-commutative version of this theorem. So let me give kind of a glimpse of the analysis of the low max degree test. It's just some sketches. So in this example, I'm just going to simplify things and assume that we're considering max degree D equals to 1. So all variables have degree at most 1. So these are multilinear polynomials. And the proof proceeds by induction on the vector space dimension M. So the base case is M equals to 1. And the argument proceeds by saying that if you have points measurements, these AXs, we can glue them together into line measurements that output univariate degree D polynomials. So, you know, for every point on the line, we have these measurements. They output values in the finite field. And what we know about these points measurements is that they pass this low degree test. So from that guarantee, we can glue them into a single measurement L that outputs a univariate polynomial. And then the induction step is just to continue pasting together measurements. So let's say we have, you know, we're in, you know, our vector space is Fn plus 1, and we're given measurements on axis parallel subspaces.
Mm-hmm.
So for, you know, so Z1 and Z2, they're you know, they index the horizontal axis. And then let's say for 2 points, Z1 and Z2, we have measurements that will output a polynomial that you know, gives you values on each of these planes. Then we can glue them together into you know, a single n plus 1 dimensional subspace measurement T that gives values for everything in this cube. So just to give a little more detail, yeah, we have these 2 measurements, SZ1, SZ2. These measurements output m variable max degree D polynomials. And we know that, let's say they have some consistency with the point measurements of the corresponding subspaces. So this S, let's say this SZ2, when we make this measurement, it has, you know, a good consistency with the points measurement given by the star. So this star is some point in the whole vector space, in this whole cube. If we make that points measurement, that's the same as making the subspace measurement and then evaluating at this point. Okay, similar for this this S to the Z12. When we paste them, how do we paste them? Well, at a high level, this measurement T corresponds to measuring these 2 subspace measurements, and then interpolating, right? You interpolate to the whole cube, and then you get a n plus 1 variable polynomial. So that's this G. So when you measure SZ1 and SZ2, you get polynomials H1 and H2. They're in m variables. H1 and H2 correspond to these 2 planes. When you interpolate, you get a polynomial that covers the whole cube. And importantly, it has this interpolated polynomial G is consistent with all the points in the entire cube. So even this green point, which wasn't on these original subspaces. The reason that we have consistency with, say, this green point comes from the fact that all the points measurements pass the low degree test. Okay, so that's the kind of the rough cartoon picture of this inductive argument. What's the main challenge? Well, the main challenge is to control the consistency error that builds up through the induction. So when you do this pasting, you get epsilon sub m consistency with the points within the subspaces, and now you have epsilon m plus 1 consistency with points in this cube. And this epsilon m plus 1 will in general be slightly worse than epsilon sub m. And if you just naively carried out the induction for m steps, this consistency error would get out of hand. So we need to do something to control this error. And we have kind of like the main technical tool in this proof is something called the self-improvement lemma. And it says the following. Let's say you have subspace measurements that are delta consistent with points measurements. So these, okay, so by subspace here, I mean, let's say you have a measurement on this entire cube. It has some delta consistency, and maybe you're not so happy with what delta is. Maybe it's a little larger than what you would like. But then you're going to go back to the original fact that your original points pass the low max degree test with high probability. Then it actually means that there exists subspace measurements that you can say something stronger, that on 1 minus delta fraction of the Hilbert space, on this nice part of the Hilbert space, they are epsilon prime consistent with the points measurements. And the important thing is that epsilon prime does not depend on delta. It only depends on the original epsilon.
When you say 1 minus delta fraction, you mean a subspace of relative dimension 1 minus delta, or what do you mean exactly?
Yeah, relative dimension. So if you took like the normalized trace.
Right, okay, so it's a relative dimension, yes, 1 minus delta, okay, good.
Yeah. So on this 1 minus delta fraction, you get, you get good consistency, and you just continue working within this 1 minus delta fraction. So this 1 minus delta fraction will shrink over the induction, but in a way it's okay. You're willing to pay that price. But the consistency is stays low. You basically reset it to a baseline value. Okay, so that's just that's a glimpse of the the analysis. It's this inductive step argument. And now let me turn to an application of this non-commutative low degree test. And it's a very important part in this quantum complexity result called MIP star equals RE. In this result, there are two main uses of the low max degree test. Actually, one of the uses is to really to use this probabilistically checkable proofs theorem that I mentioned earlier. So that's one use. The other use is to design a highly efficient and robust dimension test. So what do I mean by dimension test? Let's recall the magic square game. You have these constraints on these variables. And let's say that you have measurements AX1 up to AX9. They're binary measurements, meaning that they output 0 or 1. And let's say that these measurements satisfy the row and column constraints of this game with probability that's greater than some constant, right? Pretty close to 1. It's not necessarily probability 1, but close. This tells you that these A measurements must have dimension 4. They cannot have smaller dimension. Mm-hmm. So in that sense, the magic square test is the magic square game is a dimension test for these operators. All right. So we can come up with a much stronger dimension test, and this is what we call the poly basis test. Mm-hmm. For all n, there's a test, depending on n, such that if you have a set of measurements that is accepted with probability 1 minus epsilon, then
you get 2 to the n, yes, yeah. Yeah, you get 2 to the n because of Clifford algebras, sure, yeah.
Yeah, so you get dimension 2 to the n with some loss. The loss is poly and epsilon times poly log n. And you have the number of measurements that you use is very few. The total number of measurements in this set is poly n. So with poly n measurements, you can essentially force a 2 to the n dimensional exponential dimensional space. And it's also robust in the sense that this delta gives you a you have a non-trivial guarantee when your acceptance probability is at most 1 over poly log n. So coming up with a dimension test with both this efficiency and robustness property is pretty tricky. Like if you just wanted one or the other, that's not too hard, or it's easier at least. But getting both of them all in the same place, that requires some work, and it really uses this low max degree test in a very crucial way. So given this, one way of kind of summarizing the proof of MIP star R equals RE is you use this dimension test plus the low max degree test and this PCP theorem that I mentioned. You recursively build a dimension test for arbitrarily large dimension using a fixed number of measurements and fixed robustness. So that's one way of kind of painting what the result is. Okay. And let me end by stating a conjecture. We don't know if this is true, but it'd be really nice if it were true. So let's say you have epsilon, you have NDQ, and you have measurements that approximately commute. They pass the low degree test with probability 1 minus epsilon. And you know that there are global measurements S with outcomes that are degree D polynomials, not max degree, the original degree, such that the points measurements and these global measurements are consistent with this error. And this is importantly non-trivial for constant epsilon. So before epsilon had to be at most 1 over polynomial in M. Here, this will still be interesting for constant epsilon. So we think this is true because this would be like the, we know this is true in the classical case. Whether it's true in the non-commutative case, we don't know. You don't have to consider line versus point, or picking a random line. You can consider picking a random, let's say, 2-dimensional, 3-dimensional subspace. Sometimes that can help in the analysis. So here's a conjecture. It'd be quite nice if there was a proof of it. Other open problems. Can we generalize this to the infinite dimensional setting? So everything I mentioned, is in finite dimensions. The proof most of the proof works for infinite dimensions, but there's a couple places, such as the self-improvement lemma, which we don't know how to generalize it to the infinite.
Well, there is obviously type 2-1 factors behind the scene, because when you were talking about this normalized dimension and so on, I mean, they are just there. I mean,
Yeah. So it could be that maybe there's a easy way to extend this to infinite dimensions, but yeah, I can just say that the main sticking point is this self-improvement lemma. Somehow all the arguments that are used in our paper seem very tailored to finite dimensions, but we don't know. An interesting question that I like is whether this approximate commutation condition, is it redundant? So I've said that we need to put this here, but it's also possible that passing the low degree test with 1 minus epsilon probability already enforces this. But we don't know how to prove this. It could be true. It'd be interesting if it were true. And finally, this in classical computer science, there's a large area called property testing, where you want to test properties not just of low degreeness, but other things about functions, or other combinatorial structures. Can you also consider non-commutative analogs of this? I think there probably are, and there's probably interesting things to say about that. So with that, let me stop here, and thank you for listening.
It's an excellent talk. Yes.
Yeah, thank you very much for a beautiful talk. Are there any questions?
Yes, I have not a question, but a comment, because, okay, this question that you resolved, MIP star equals RE, I mean, as you know very well, it is implying that the problem which I had formulated a long time ago as a negative answer, which was the embedding problem. But I insist on the fact that I always formulated it as a problem, and I insisted when I was, putting on Wikipedia and all that people call it a problem, because the honest truth is that I never really had any feeling in one direction or the other. What I found out is that immediately when I found this condition, I found that it was true in some cases which are not hyperfinite, like free groups and so on and so forth. But then at no time could I, sort of have any intuition of whether it would be in one direction or the other. So for that reason, I mean, of course, I know that it's better to call it a conjecture when you sort of, but somehow, this doesn't correspond to the truth. I mean, the truth is that I never had, and it's the same for Tyrrellson. He called it a problem, and I think he was very right in that way. So, I mean, obviously, it's an extremely delicate question, I mean, one could see in your explanations where the 2-1 factor was coming up. I mean, the one which is not embeddable in the ultra product of the hyperfinite. Exactly because of what you were doing with these two conditions, which were almost contradicting each other, you know, and then I think if you build this in a tower, you will get a counterexample somehow.
Uh-huh. Oh, that's great to hear it from.
Well, okay. I mean, this is just this time. It is really an intuition, but of course, you know.
I mean that the mention that you didn't think, because people have asked me, did you believe that it was true or not? And I said, well, I'm not really sure, but I've heard people mention as a conjecture. So, it's good to know the truth.
I mean, it was you know, it was an obvious question, but then okay, since I didn't have much direct interest in it, I never, you know, sort of even really thought about it. But okay, what I found marvelous was the connections that other people have found, like you know, Kirchberg and then Tyrelson and so on. So this I consider as absolutely marvelous work. But then it seems to me, so in fact, I mean, the first proof was not quite right, and then you had to make a better proof for this MIP star equals RE. I mean, how are things concerning this? I mean, it relies on your last type of work. Eh? Yes.
Yeah, good question. So the error was actually we thought this conjecture was true.
Yeah.
So that was the assumption because you know, some earlier work of some of the authors
yes.
had established this, but it turned out there's an error in this analysis, yes. And we had to prove the weaker one, the one with the, but it's still sufficient for.
Yeah, if I understood well, I mean, there was a problem with this compensation technique that you had, or something like that.
Yeah. Basically, it comes in this. So basically comes in this. So here,
yes.
we say that there's 1 minus delta fraction in the Hilbert space that's good, but then this delta or this good fraction shrinks. For us, it's okay, but this conjecture, the stronger version actually, this delta fraction or this 1 minus delta fraction does not shrink.
I understand.
Yeah,
I see. Yeah, of course, it's very important that it doesn't shrink. Yes, sure. Okay. Or at least you mean that it doesn't shrink to 0.
That's right. Yeah.
Sure. Yeah. Okay. Yeah. I see very well. Yes. Okay. Well, okay. That's I find it quite amazing that starting with finite fields and so on, you know, you end up with this. Can you say intuitively what does it mean? This MIP star equals RE? I mean, what is it? What does it say really? I mean.
I mean, so from the definition, it's a statement about these, it's about proof checking in a specific model of proof checking when you have quantum entangled provers. So, so I think you mentioned Merman's game, right?
Right.
So sure, this is like one of these Bell experiments, describing a Bell experiment.
Sure. So what does it mean? It means that if you are able to, if you're allowed to use the quantum, you cannot do better than you would do classically or something like that?
No, it says that in this model of if you have quantum entangled provers, that they can, that a classical verifier can verify whether by communicating with these quantum provers, by running an experiment with them, can verify whether a statement in ZFC has a proof or not.
I understand, but so what does it say about the quantum prover? I mean, is it helpful or not?
Oh, yes, it is very helpful. The entanglement helps them prove to you very strong statements.
I see. Yeah. I see. Okay, well, yes, that's very nice. But so what do these initials mean? MIP, you know, and RE. I mean, what is the spelling?
So MIP stands for, it's a name of a complexity class. It stands for multi-prover interactive proof.
And interactive proof, I see. Interactive proof.
And when it has a star, yeah, it means that you have two or more provers that can share quantum entanglement.
They share by quantum entanglement. Yes, I see. I see. And the other side, RE, what does it mean?
RE stands for the class of recursively enumerable problems,
Okay.
which is a notion in like computability and logic.
I understand. I understand. So what you are saying is that the two classes are the same. What was known before the equality?
So for a very long time, it was just known that MIP star was contained in RE.
I see. Okay.
But that's not saying anything really interesting, because it just means that.
Sure. Yeah.
Yeah.
Yeah. It's kind of obvious. Yeah. Okay. Yes.
Can I make two comments?
Yes, please.
So the first one is in terms of finding an actual 2-1 factor which does not embed into R omega. I'm not sure if he ever wrote this down or not, but Sam Kim, who's at Waterloo, let me know that from a correlation that separates the two sets of correlations in Searlson's problem, one can constructively build a 2-1 factor which doesn't embed into R omega. So it's as constructive as it is to find a counterexample to Searlson's problem, which, as far as I know, isn't constructive right now. But then the other thing I wanted to point out is a shameless plug, considering that Khan himself is here, is that the path from MIP star equals RE to the failure of CP uses the equivalence with Searlson's problem and Kirchhoff's
it uses
problem.
Yeah.
But in a paper I wrote with Brad Hart, we actually show how to go directly from MIP star equals RE to the failure of CP using basic model theory. And our main result more or less states that if you want to know how to approximate traces of star polynomials in R by going up to large enough matrix algebras, you cannot do that in any computably efficient way. And that follows from MIP star equals RE, and that in turn allows you to show that the CP is not true.
Sure. Okay. That's very clear. Yeah. Okay.
So Henry, does your method like tell us how to construct like a group counterexample to Alan means embedding problem?
I think it's almost automatic. Yes.
Yeah,
because any 2-1 factor you can come from. Well, okay. I mean, yeah, you can embed into.
So it's kind of interesting because. Okay, I'm not an algebraist at all. I don't know much about it, but from what I understand, what we prove is the existence of such a group or factor, but we don't give an explicit we don't know how to give an explicit description of it.
I thought that you don't know if there's a group counterexample.
Sorry, yeah, we don't know if there's a group counterexample, but in terms of whether there's an algebra counterexample.
Yeah. So, yeah, I just wonder about, this, if there's a group, maybe the geometry of the group is so sophisticated, it can be.
It should be very sophisticated.
to study some of the other problems we are interested, like the Novikov conjectures.
Yeah. It should be kind of a monster in that sense, yes.
Yeah, it should be a monster in some way.
Yeah, but in a way, what it does, it sort of singles out a certain class of factors, which are sort of, of groups, which are accessible from finite dimension, which is, okay, somehow quite different from.
Yeah.
So, I mean, but okay, but from what I understand, I mean, this proof is very complicated, very delicate. I mean, and, very, very sophisticated. I mean, it's and it truly relates to the fundamental difference with quantum mechanics. I mean, because this, I don't know if you know this lecture of Coleman, which is called Quantum Mechanics in Your Face. Well, you should look at it. You should look at it because it's called Quantum Mechanics in Your Face. It is available on the internet. And it is extremely enjoyable because he starts by explaining that, you know, he hesitated in giving his title so he was communicating his title for a Dirac lecture. And the first title he gave, it was not accepted because he called it, it's quantum mechanics, you idiot. And then, okay, then he modified it and so on. And I mean, the lecture is wonderful because he explains a mere mean example, but he addresses, if you want, an aging professor who never liked quantum mechanics. and so, I mean, and the lecture is extremely enjoyable. For instance, 15 minutes after the beginning of the lecture, so in the first 15 minutes, he explains the basis of quantum mechanics. And after 15 minutes, he asks to the audience, if anybody has any question at this point of the lecture, please leave the room. So I'm sure you would enjoy this lecture tremendously, you know, because so I mean, he gives the example with 3 spin systems, and where, you know, you do several measurements, and because of this magic square, what you find out is that whereas classically you would expect the product of 3 quantities to always be equal to 1, in the quantum mechanical framework, so product is always equal to -1. So I mean, but if you go on internet and you put Coleman quantum mechanics in your face, you'll get it. I mean, you know, it's on YouTube. It's a great lecture. It's really a wonderful thing, really.
Well, yeah, thanks for the recommendation. Yeah, I'll have to look that up.
I have a quick question, Henry, if you still have time. I don't know what time the seminar officially ends, but I just have a quick question. So as you've heard probably like me ramble about before, like Marius Junger stuff, we've always liked this kind of trilinear Kirchhoff conjecture, right? So when you think about, I think this would have came up at Banff last 2019 summer regarding CEP and such, where if you recall, the equal formulation with CEP was, of course, having this full group C-star algebra of the free group of countably infinite many generators, right, had weak expectation property, yes? And then there was this question where, you know, the equivalence of this was if you take the tensor product of both of those full group C-star algebras, if min was equal to max, you know this. So then the natural thing was what happened with, you know, 3 tensors, if I did 3 now, or I do any number of them. And I think this came up at this conference. Now, do we know anything now more about some of these situations? Because I think even Thomas Vidic had mentioned to me some of these, like you all were able to get it down to a certain number, saying, well, we don't think it's going to work here, or any updates on because we have the recent work of all of you regarding this question now?
I don't know if there's anything more to say. I mean, beyond, I guess, the straightforward implication that it's also, you know, they're not equal for if you have tensor product of 3 things. Mm-hmm. Yeah, I'm not like, what more would you want to say? Or, I mean, I don't know if anything more that could be said, but did you have something in mind?
No, just kind of curious about, no, it's fine, no.
I guess one possible question you can ask is if there's an easier proof for say 3 factors or something like that. But I don't know if that's possible. Mm-hmm. Yeah.
So are there any other questions or comments? If not, let's thank Henry for a beautiful, very inspiring talk. Yeah, thank you very much.
All right, thank you.
Thank you.